Okay, cool. So the first things to note, just again about schedule, is so next week things are a little bit different. In particular, we have lecture next week on Monday at 10:45, and then the tutorial is the usual lecture time. I don't know the rooms; they're on my timetable. You guys should be able to find them, but I just wanted to flag them up. Um, this is because I'm hosting a conference on Thursday and Friday of next week, so I won't be able to do tutorials and things. So we've moved those a little bit. Then the week after, so this is next week. The week after, week 39, I guess it is, there's no tutorial on the Friday. Instead, we'll have two tutorials the week after. Thankfully, that'll be okay. I'll push the homework that would normally be what we'd go through for this tutorial back a week, so you'll have time to kind of do both of them together. The other nice thing is actually the two tutorials fit nicely together because, well, as you're going to see very shortly, we're going to go ahead next week and start in our second formal language. So having both of them kind of back to back won't be the end of the world. I think the tutorials in week 40, so in 2 weeks' time, are one's on Wednesday and one's on Friday, the usual time. But I'll let you know on the closer things. Again, always check my timetable, it's just helpful. Before we go back to our regularly scheduled programming, any questions on that? Is it kind of clear? I'll remind you all on Friday as well in the tutorial, but I just wanted to go ahead and flag it up now. Cool. Okay. So nice. Good, and I've got my recording going. I guess, well, I've also got everybody's attention. Has anyone actually, like, watched the lecture recordings? Are they okay? Okay. Again, I've done a bunch of recordings at home. Don't really like doing the recordings here during the actual show, but it is what it is. So, nice to see everybody. I hope you guys all had a lovely weekend. So what we're going to do today, as I kind of promised at the end of the tutorial on Friday, is we're going to talk about evaluating TFL sentences. That is, determining when they're going to be true or false. So just to jump straight in, basically what we're going to start off with is to talk about the underlying idea. So TFL is called TF for a reason. That is, it's truth functional. The most important thing throughout this whole language is that complex sentences, their truth values, are functional. That is, they depend upon the truth values of the atoms. And all the connectives are set up to kind of let that happen. So we'll talk a little bit about the basic idea, and then we'll go through connective by connective, talking about how they work. What we're going to have is what we'll call characteristic truth tables for each of the connectives. We've already talked a little bit about this when we're thinking about when a conditional is true or false and things like this. But we're going to have specific tables for each connective. And then once we have those, we'll be able to generate what we'll call complete truth tables. That is, a table for an entire sentence, where what we do is fix the truth value of the atoms, and then at each stage, they fix the progressively more complex sentences we've generated until we have the whole thing. Basically, I'm going to teach you how to draw your own Excel sheets. Yay! Lots of T's and F's. Though there's all for a reason. And the reason is the big payoff. Basically, these truth tables are going to give us an ability to recapture a bunch of those concepts that we talked about in the very first lecture. So remember things like joint inconsistency, unnecessary truth, and things like this. We're going to have formal ways to characterize them purely in terms of our truth functionality. And then the real big payoff is we're actually going to have a way to track validity. And we're going to do it entirely just in terms of these tables. That'll be the big plan. If we have time at the very end, we'll talk a little bit about some shortcuts and how to just kind of save yourself some time constructing tables. But the big thing for us is going to be, again, just kind of getting clear on how tables work, what they're meant to do. Cool? Other thing I forgot, should have mentioned a second ago, how do we want to do the session? Do we want to go for a bit and then break, or go for a bit and then end early? I saw nods for break already. Is that okay? Go for a break? Cool. So we'll go, again, you know the drill. 9:30-ish, give or take, and then we'll take our break and then come back. Nice. Cool. So let's talk about truth functionality. So we know, we talked about this several times now, that any non-atomic TFL sentence is going to be composed of atomic sentences linked up with the various connectives, right? That's just how we build the sentences. Think about the sentential construction rules. Well, this lets us actually offer a definition of truth functionality. We can say a connective is truth functional if and only if the truth values of a sentence featuring that connective as its main logical operator is uniquely determined by the truth values of the relevant atoms. So again, the basic thought is we fix the truth values of the little teeny tiny parts, and then it fixes the values of each more complex thing all the way up until we get to the main logical operator, the one we added last. And here's the cool thing. Every connective in TFL is truth functional. That's why it's called truth functional. That's why it's called truth functional logic. So to determine the truth value of a TFL sentence, you only need to know the truth values of the basic constituents, the atoms. It inflects upwards, which is very nice. So more than that, to be really blunt, and this is one of the reasons why all we've been doing is something like symbolizing, the connectives are just simply truth functions. That's it. All they do is they take in truth values and they spit out other truth values. They're not tracking anything like meaning. They're not tracking anything like implicature or nuance or tone that we might have when we think about the relevant kind of connectives in natural language. I should say, do people know what I mean when I say things like implicature? So this is where we say something without actually asserting it. It's kind of conveyed by maybe the tone or the particular arrangement or how things go. So to give you an example, I think I mentioned maybe this once, right? If I say Brittany had a baby and got married, there's a kind of implicature there, a conveyance, that there's a temporal ordering. She had a baby, and then there was a shotgun wedding. Okay. But of course, that's not strictly in the sentence. That's kind of conveyed by the choice that I made to structure the conjuncts in that way. It's not said, at least explicitly, but it's said in some kind of looser sense. Do we get the kind of feeling there? Again, the other typical example is if someone asks you for a letter of recommendation, and in the letter of recommendation, you just talk about how good they are at tying their shoes. What does the letter of recommendation then convey? Well, it kind of indirectly says they're not really very good and you probably shouldn't hire them. It doesn't say that, but it conveys that. There's an implicature here. When we go to TFL, that goes away. There is nothing like implication. There's nothing like nuance or tone or anything. We don't care. We just care about pure, raw truth functionality. Taking some truth values in and spitting some other truth values out. This is, again, why when we're going from natural language to TFL, it's not a translation. We don't care about any of these things. Because, to be honest, a really good translation should try and capture as much of this as you can. Not just capturing meaning, but you also want to capture the implicature, the nuance, the tone. This is why, say, translating poetry is so difficult. Because if all you wanted to do was just capture the kind of meaning of each line, cool. But then it feels like you kind of lost what was maybe most important about some of these constructions. So TFL is fundamentally unequipped to deal with meaning. It is not a good language to translate with. But that's cool, because that's not what it's meant to do. is merely meant to track this kind of truth functionality. And that makes sense, because remember what we went in with, what were we hunting? So we started off by thinking about validity. And validity was basically defined as, not basically, it was defined as, it's impossible to make all the premises true and the conclusion false. We didn't talk about meaning. We didn't care about that. We just talked about whether these can be true and this can be false. Validity, as we initially got it, was defined in a purely true functional way. So unsurprising, our first stab at capturing it is going to be purely concerned with true functionality. Indeed, I suspect this is one of the reasons why some people have such a weird time with that Mars is moons style argument. Surely that's not valid, because the premises have nothing to do with the conclusion. Cool, that's not what validity is about. Right? It was just defined in terms of this notion of follows from. That is, whenever these ones are true, so is this one. So truth functionality is our first attempt to capture that. So we might then say, when we treat a TFL sentence as symbolizing an English sentence, we're stipulating the TFL sentence has the same truth value as the relevant English one. We don't care what it means, or that it has the same meaning, just that, hey, if this one's true, so is this one, and vice versa. That's the big trick. Okay. Cool. So, as we mentioned, any non-atomic sentence of TFL is composed of atomic sentences linked by sentential connectives. In TFL, the truth value of a complex sentence is entirely determined by the truth values of the atoms that compose it. Now, exactly how this determination goes is going to be determined by the relevant connectives in play. And each connective is going to have a specific kind of table that defines its function. That is, it's going to say, hey, when you spit in these values, this is the value you get out. So let's talk about the characteristic tables for each of the connectives. So what we're going to be able to do is we can depict the truth functionality of each connective using a table. These are going to be tables of truth values. Specifically, we're going to use T and F to abbreviate truth and false. Shock, horror, I'm sure. Note, you can also use 1 and 0. I don't really care, as long as you make it clear which one is the true and which one is the false. Importantly, note that these occurrences are not expressions of TFL. They're expressions in a meta-language. We're talking about sentences in TFL. So, let's put some terminology here. Our truth table is going to consist of valuations. A valuation is an assignment of truth values to particular atomic sentences. And our table is going to consist of rows, so one's going across, and columns, one's going up and down. Each row, each one going across, is a valuation. That is, it's a stipulated collection of truth values for some atoms. So I'm going to say, hey, here's one valuation. A is true, B is true, C is false. Each column is going to be a collection of valuations. In fact, what we're going to often have is a collection of all possible valuations for the relevant atoms and for the relevant truth functional connectives. But again, a valuation is a stipulated truth value for an atom. Row of a table gives you a particular one. Columns gives you collections. These tables then basically give you a way of figuring out the truth values of the bigger things from the valuations. So here you go. Here's our first one. It's our easiest, our simplest characteristic truth table. It's the characteristic truth table for negation. And it's really easy. Negation is one place, right? It only takes one sentence. So, here's what we have. If the sentence we're feeding in is true, then the sentence we get out, the negated one, is false. And vice versa. If the thing we feed in is false, then the thing we get out is true. Makes sense, right? Negation basically just flips truth values. So far, so good. So note, this is a lovely one to start with because it shows us exactly what we have. We have one valuation where we assign, let's just treat this as an atom, A to be true, then not A as false. Alternatively, if we assign A as false, then we get out A is true, not A is true. Again, easy peasy right off the bat. Let's look at conjunction. Here's conjunction. So conjunction, remember we talked about the grammar. Conjunction always has two sentences on either side. So that means it's going to be true or false depending on what happens with the ones on both sides. So, what kind of combinations could we have? Well, we can have the one where both sides are true, where one side's true and the other is false, where we flip them, or where they're both false. Before we go on, do we see how that exhausts the possibilities? Again, that's literally just all of the different combinations of basic truth values we might have. So we can draw this table. And this table gives us all of the different valuations. And note the columns here. The columns are telling us, hey, here's all the possible valuations. Every possible assignment of truth values we might have. So when is A conjunction be true? Well, to put it really bluntly, if both sides are true. Otherwise, it's false. Which makes sense, because remember, what's conjunction supposed to capture? It's supposed to capture something like both and. Brittany had a baby and she got married. When is that true? She's got to do both. If she just got married and didn't have a baby, well, then the and claim is false. If she just had a baby and didn't get married, again, the and claim is false. And then finally, if she didn't do any of it, why are you lying to me? So our table is capturing that idea. Again, what does it do? It lists off the combinations for the atoms, the things that we're feeding in, and then tells us what the value would be for the thing we're getting out. Make sense? Nice. If we've got this, we've got it. Basically, all we're going to have to do is just think about the different functions for the different connectors. So negation just does a flip. Conjunction is one where it's only true if both are true. Here's disjunction. Disjunction, unsurprisingly, is much easier to please. It is going to be true if even one of the two sides is true. So if both A and B are true, cool. A or B is true. A is true and B isn't, nice. The same thing the other way. The only time it's false is if they're both false. So again, comparing conjunction and disjunction, conjunction is hard to please. To go back, you have to have both. Disjunction is easy to please. If you even give it just one side, it's happy. Now here's the thing. We've been kind of treating it as if the things we can feed in are just atoms, but of course that's not true. The things on either side of the disjunction might themselves be complex sentences, but the function still works the same. Whatever truth value that part has, that disjunct has, is still going to play the role that we want it to play for the truth function. This is just preempting what we're going to do in about 20 minutes, where we're going to have one big table with all this stuff together. Okay, so we good? Negation, conjunction, disjunction, so far so good? Here's our first really easiest one. Oh, no, sorry. I gave you the easier one first. The biconditional. So we'll switch the order. The biconditional is kind of funny. But it's just kind of funny. Right? It says A if and only if B. So when is it true? Well, it's true if both sides have the same truth value. No, it doesn't matter if they're both false or if they're both true. It just requires that they have the same on both sides. So what this means is that much like conjunction and disjunction, the biconditional is symmetric. You can flop the sides, it does not impact the truth value of the thing. Cool? Here's the one to remember, and this is one, years of doing this, people always forget, is this bit. The biconditional is also true if both sides are false. So it's just that it has to have the same truth value on both sides. They can be both true, or they can be both false. Here's the conditional. We talked about it, but let's go through it one by one, because the conditional is the funny one. So we have 4 possibilities. If both of them are true, then a conditional is true. If the first part, the antecedent, is true and the consequence false, the conditional is false. If the antecedent is false and the consequence true, the conditional is true. And finally, if they're both false, the conditional is true. Now that's weird and hideous, and I imagine many of you might be like, what the fuck? So let's ask, what's weird about this table? What do we think? What's weird? Yeah. The third row is kind of weird, right? It feels strange that if, like, the first part's false and the second part's true, then the conditional still kind of goes. Because it feels like the conditional is saying, hey, the second part, like, depends on the first. So let's draw out 2 oddities about this table. Here's our first oddity. We're going to call them paradoxes. Though they're not strictly speaking paradoxes in the sense that you have something both true and false. First thing to note is, whenever the antecedent is false, whenever the first part's false, the conditional is always true. So this is a true one. If there are exactly 50 people in the room, then there are exactly 5,000 people in the room. This is a true conditional. Because we have nowhere close. Which seems weird. Right? Similarly, right, if we have exactly 50 people in the room, then there are exactly, I don't know, let's say 21 people, give or take. Let's just suppose that's how many there are. That would also be true. And that seems weird and bad and creepy. Here's the other weirdness. Whenever the consequent, the second part is true, conditional is always true, regardless of what happens in the front. So if Nathan is a professional footballer, then Tilburg is in the Netherlands. True, though sadly the antecedent is not true. I took an arrow to So that's weird. That's weird. Again, if the back part is true, then it's just true. Now we can explain the weirdness, and in fact we talked about this twice in the tutorial, so this is going to be a little bit boring. These are paradoxes because they're violations of our intuition, But we might wonder why adopt this kind of understanding of the conditional if it throws up these oddities. So here's the kind of motivation. The core idea of what we're trying to do is to build a formal language consisting of atoms, base units, and then truth functional connectives. And it's designed to make sense of when arguments are valid or invalid, good or bad, right, in virtue of their form. Remember, that was what we were after. Just thinking about goodness in virtue of form. We'll get to meaning next week. And we've already just stipulated connective is truth functional if just the truths of the parts kind of come up. If we want a truth functional treatment of if then in English, just to put really bluntly, this is the best fucking option we have. Everything else sucks. So here's a case to try and get you as to why this is the best option. We talked about this before. Think about the promises. I promise you that if I'm healthy, then I'll come to class. This originally was from Kyle Friendly, but I think it's just such a wonderful example. If I'm healthy, then I'll come to class. When is the promise broken? There's 4 cases. If we think about the first one, it's pretty clear that the promise is not broken. It's kept. If I'm healthy and I come to class. Second one, if I'm healthy, but I decide to blow class off, then I've clearly broken my promise. Third one, well, if I'm sick and I show up to class anyway, like the hero that I am, right? Well, then I didn't break my promise. Again, I kept the promise because the promise was, if I'm healthy, then I'll be at class. So if I'm sick and show up, cool. Right? Going above and beyond the call of duty. Promise still kept. And then, of course, if I do the smart thing, if I'm sick and I stay home, well, then I haven't broken my promise. The only time we break the promise is, again, if the first part's true and the second part's false. Here's the neat thing. We can see the promise breaking as parallel to a truth function. The truth function says, hey, if the first part's true, the second part must be too. That is, if you've got truth in the beginning, you won't lose it in the back. Note, if that's what we think if then says, this is exactly what we want. We can map it right back. That is, whenever first part is true, second part is too. So what happens when the first part's not true? Cool. What you said is just a vacuous promise. You've kept it, but you've kept it on a kind of technicality. Unlike the top two, where, hey, cool, we started with truth, and either we didn't lose it, or we didn't. Again, this is the best we're going to do if we think that the if-then is genuinely something that's truthful, that's about, if you start with truth, then you get truth back. So, this is the characteristic truth table for the condition. It's false only when the antecedent is true and the consequent is false. It's true every other time. That's it. That's the 5 characteristic truth tables. Basically, we can use these to now generate any kind of truth table we want for any complex sentence. So the paradoxes here are striking because the everyday English version of if-then presupposes a kind of connection or a meaningful connection or a relevance between the antecedent and the consequent, but that's not going to be captured in a merely truth-functional sense. Just as a flagging note, this is something that will come up, I think, in other courses, in particular philosophy of mind. English also allows for a different kind of conditional. This is the subjunctive or counterfactual conditional. to get a sense for the difference, say if Oswald if Oswald didn't shoot Kennedy, then someone did. No, this has to be true. And why is this true? Because somebody shot Kennedy. And if it wasn't Oswald, then somebody did. This is an everyday if-then conditional. Contrast that with our second one. If Oswald hadn't shot Kennedy, then someone else would have. What's different about this one? So this presupposes that Oswald, in fact, was the one who shot Kennedy. And then says, hey, imagine that Oswald hadn't done it. Well, then the dude on the grassy knoll would have been there to take up and clean up the mess. The CIA sniper, or the Cuban, or insert your favorite conspiracy theory here. So the second kind of conditional says, suppose something that isn't the case were true. What would then happen? Do we kind of feel the difference between the two? So our first one says, right, fact, fact. If it's a fact Oswald didn't shoot Kennedy, then it must be a fact that somebody else did. Our second one says, hey, let's suppose this thing that I know to be false were true. What would then follow? What would have happened? It's a very subtle difference in the English, but I think conceptually you can kind of draw them out. Here's another one. If kangaroos didn't have tails, then they would topple over. So what am I saying? I'm saying something about the shape of this animal, and it's were they to have somehow come into existence without this big tail thing at the back, they would just be constantly on their sides. Not that they are in fact constantly on their sides. That's this kind of thing. It's a question about what would have happened had this other thing taken place. Counterfactuals are very interesting. We'll talk very, very, very briefly about them in the second half of the course. We are not going to be able to get to a point where we can quite make sense of it. Because they're not true functions. There's no way to make sense of these true functions. But it's helpful to see the contrast. We're only ever going to deal with the topics. Okay. So, let's stitch together this stuff that we've done. We have the characteristic tables for each one of the connectors, and we know that every TFL sentence is going to be built up using those and only those connectors. So here's the really cool part. We can just start to expand our table. Because all we have to do is figure out what the truth value of each relevant part is, and then we can use a version of the characteristic table for each operator. So, we'll say a complete truth table has a line for every possible assignment of true and false to the relevant atomic sentences. And each line represents a valuation. Complete table has a line for all possible different valuations. Put another way, a complete table is going to list all possible assignments of truth and falsity to the relevant atomic sentences. The size of the complete table depends upon the number of atoms we're going to pay attention to. So a sentence containing only one atomic sentence is going to have 2 rows. Makes sense, because the relevant atom could either be true or it can be false. Those are the 2 options. If we have 2, we'll have 4. Because A and B can both be true, A can be true and B can be false, A can be false and B can be true, or they can both be false. Just think about the characteristic tables we had a second ago. They had 4 possibilities. What happens if we have 3? Well, then we'll have 8 rows. Because what we need to do is list every possible combination of truth and falsity for each atom. So by listing the 8, what we get is an exhaustive collection. These are all the possibilities. Just to kind of give you the general one, if a sentence has n different atoms involved in it, then we'll have 2 to the n rows. Don't need to know this, it's just sort of. So, we might wonder how to fill in the kind of list. How do we get all the valuations? Well, here's the easiest thing to do. What we need to do is list off the atoms. Pull them out from the sentence we're doing. We did this at the very end. Remember exercise C on page 28, I think it was? When we pulled out, we talked about the sentence construction, and at the very bottom, there was H, I, J, and K. The atoms, we build it up. So here's how we start. You list all of the relevant atoms. Doesn't really matter what order you put them in. And then we're going to start assigning the truth values underneath them. And this is a suggested way to do it. You start off by just alternating true and false on the rightmost one. Then, for the next one over, you double it. 2 truths, 2 falses, 2 truths, 2 falses, etc., etc. And then for the one over to that, double it again. 4 truths, 4 falses. And then if there's another one, you go to 8, 16, 32. You see how this goes. What we're doing, this little description here, is a mechanical way to make sure we get every possible collection. It's easier to see with an example. So suppose we have a sentence that involves 3 atomic elements, 3 atomic sentences. And we want to get all the possible combinations of truth values here. What we could do is you start by flipping back and forth. Then for our next one, you just double it up. And then for our last one, double it up again. Here's the cool thing. What have we done? Right? Each row represents a valuation, an assignment of truth values to some atoms. And if we look at this matrix, this is all of the possible valuations. All the combinations that we could have for these 3 atoms. Don't stress too much about this, but do more practice on it. But the first thing I want to ask before we go on, do we see why it captures all the valuations? Cool. So when we're constructing a complete truth table, this is our first step. We basically want to make a matrix of all the valuations, all of the relevant valuations. So here we go. Here's an example. Let's build a complete truth table for this sentence. What do we do first? I've already pulled out the relevant atoms for you. Where would we start? Nice, right? So we're going to fill out this part. Effectively, this part is our matrix. It's listing all of the relevant valuations, all of the assignments of truth values. And how can we do it? Well, I gave it to you just a second ago. We can start off by first filling in the rightmost one. And note, it doesn't matter the order that we actually wrote them in. We don't care about that. Happens that they're in alphabetical order here, but they could be in some other order instead. So we fill in our first one by alternating truths and falses. Cool. And then we go to the next one. We fill it in, we double it. 2 truths, 2 falses, 2 truths, 2 falses. And then the last one, double it again. 4 truths, 4 falses. By following this mechanical procedure, we generate this matrix, which has every possible assignment of truth and falsity to the relevant atoms. If you follow the procedure, there's no way you'll miss one out. No, you don't have to follow the procedure. You can just start writing P's and F's as you like. But this is a handy way to make sure you never miss one. Now, what do we think we do next? If we're going to make a complete table for this sentence. Well, let's think, right? What are these? What are these columns? They're listing the relevant truth values that these atoms have for each valuation. That is, they're saying, hey, here's a truth value that this atom could have. Here's a truth value that this atom could have. Here's a truth value this atom could have. So we just copy them over. We copy the column underneath each relevant atom and plug it in to where it occurs in our full sentence. Now, why would we do that? Because what we can do next is start using the characteristic truth tables. Because all that's left are the connectives. And the connectives, we know how they work. We were told with the characteristic tables. So all we have to do now is think about what sentence did we build next. So what's the next level of complexity? Obviously, when we're constructing this sentence, we started with these atoms. What did we build next? Yeah, right? Those were the parts that we built next. And then, of course, we use those two parts to get to the conditional. So what we need to do next is figure out what values go underneath here. Let's fill in this column. Again, we're kind of thinking about it in terms of building the Lego up. So this is the next level in the Lego. What values are we going to put in here? Let's take our first block. It's a negation. How does negation work? What was the characteristic table? You remember? About 10 minutes ago. What's negation do? If you feed in something that's true, what does negation spit out? It flips it, right? Yeah. So, what goes in here? I heard it. Yeah, it's false, right? Because we're feeding in a T, so we're going to get out an F. How about for the second one? Yeah, right? And so on down the line. You take what you're feeding in, you think about the characteristic table for the relevant connective, and that tells you what value to fill in. Basically, in this case, you get this. Where what we do is, because it's negation, whatever value we feed in, it spits out the opposite. Cool? Can you see the idea? Nice. Okay, so we managed to do the negation. What's next? Let's go back. What was the bit you meant said a second ago? What else did we do? What was our kind of first bits of construction? You know, it was doing the negation. What was the other one that we did? Yeah, the conjunction. Right? So for the conjunction, what we do is, again, we use the characteristic table, and we look at the two parts on the sides. In this case, it's going to be A and B. And we use the characteristic table we talked about a few minutes ago to fill in what's in here. So what do we do for our first valuation? What's the truth value for the conjunction here? It's true, right? Because conjunction is true if both sides are true. And the same thing for our second one. Cool, right? And how about our third one? It's false, right? Because remember, the characteristic truth table for conjunction, it's only true if both thumbs are up, Both sides are true. If even one's down, the conjunction's false. All the rest are false. Nice. Cool. What's next? Conditional. Yeah. Cool. Now here's the question. The conditional we know is going to use the characteristic truth table for the conditional, which we already know is a bit fucking. Fine. But what lines are feeding in? So look, for the conjunction, we knew where to look. It was these two. For the negation, we knew where to look. It was this column. Which columns do we look at here? Yeah. These two. Right? Here's why. Think about the construction order. We started with atoms, and then we built these two sub-sentences. And we've now got the values that they have, and they're the ones that will feed into our last step, the conditional. So we look at the T's and F's in these two columns, and they will tell us what to fill in here. Yeah? So, how about our first valuation? What's the truth value of the conditional? Well, let's check, right? Remember, when is the conditional true and when is it false? The one time the conditional is false, right? The one time it's false is if the first part's true and the second part's false. And if we look, and again, our first part's true, but our second part's false. So, it's going to go like so. False at the top, every other one. Yeah, no. The conditional is the tricky one. Cool. Okay, look what we do. We built a whole table for this complex sentence, admittedly not that complex, using each particular step. We generated a matrix. The matrix tells us the relevant truth value combinations, the valuations for each atom. And then we copy them over. We use the characteristic tables for each connected in the order that we would have constructed the sentence to then get us up to the values underneath the main operator. How cool is that? Kind of neat. Okay. Before we take a little break, we'll pause, ask questions on the steps, questions on the truth table? Yeah. Good. I'm going to go back. Tab through all of these stupid things again. Almost there. There we go. So here's the trick. Right? We start off, the first move is always to pull out all of the relevant atoms, and then count it up this way. So if there's just one atom, just 2. If there's 2, 4. If there's 3, 8. If there's 4, 16, etc., etc. That's just something you have to kind of figure out. This is the rule for it. Just between friends, I will never give you a sentence that's got more than 4 in it, because frankly, I do not want to read that many. But it's important that we understand how the process could go on indefinitely. Good. So that's always our first step. That's always our first step. Pull the atoms out, make the matrix, and then start filling in the rest of the table. And the things to remember with filling in the table is you just use the characteristic truth tables we talked about earlier. Just look. The values of the parts you're feeding in will tell you what letter to write there, whether it's a T or an F. And the other thing to be careful of, this is the problem with using distinct slides here, is always to be careful about which columns are feeding in. That is, which ones to pay attention to. For here, it was these two, because those were the ones that were one step down. They were the Lego that we connected using the conditional. Nice. Okay, let's take a break. We'll take a 10-minute break, and then we'll come back and do some more. Okay? Cool. So let's go to 45. Give or take. And yeah, cool.